Welcome everyone. So today we have a pretty straightforward problem from TIFR question paper. So the question is very natural. So generally what we have seen is that if a group is cyclic, then every subgroup of it has to be cyclic. The converse part is not at all true, that we know from some of the examples that we have actually encountered before for finite groups. So for an example, like in this problem, there are two things: that is does the infinite group play any role or not? Because if the infinite group is being cut off from this statement, then it is of course false, right? If every proper subgroup of G is cyclic, then G is cyclic or not. So one of the examples are, you take S3. Okay, so you know that this is a non-abelian group, hence it is not cyclic. So S3 is not cyclic, right? But what are the orders of the proper subgroups of S3? So orders of the proper subgroups of S3 are 2 or 3, right? So we both know that if it is of prime order, then it has to be cyclic. So S3 is a cyclic group, that is a finite cyclic group, which does not have any which is not a finite cyclic group, which has every proper subgroup cyclic. But now we cannot actually use this example because of this infinite thing. So now the question is a little bit more delicate. The question asks, does there exist an infinite like this? So the answer is the same, that yes, there exists even non-cyclic abelian group G whose all proper subgroups are cyclic. So why I actually try to include this thing as well is that it might be even abelian. Okay, so group G, which is infinite, we are now talking about all infinite ordered groups. So it is an infinite ordered abelian group which is not cyclic, but every proper subgroup of it is cyclic. Okay, so the example to this is this group. So take G to be the collection of all Z belongs to C such that Z to the power P to the power N is equals to 1 for all N belongs to natural number. So that means it is practically the collection of P to the power nth roots of unity. So G is the collection of P to the power nth roots of unity for N belongs to N. So this is as simple as that. Okay, so now what is so special about this group? The thing that is so special about this group is that every proper subgroup of it has to be finite. So this is the first observation. The observation is every proper subgroup of G is finite. Okay, because see one thing, that if we talk about subgroups of G, first of all, it has to be subsets of G, right? So whenever we have subsets of G, so suppose let's take S be a subset of G. So then this S, it contains elements like these, like, I mean, if I am talking about subsets, not subgroups, like some Z to the power P to the power K, Z to the power P to the power L, and so on and so forth. Okay. But if the moment it becomes a subgroup, the moment it becomes a subgroup, what happens is that every subgroup of G is finite. And interestingly, the subgroups are precisely the P to the power nth roots of unity for a fixed n. So suppose for a fixed n, the observation that you have to make here is that all the subgroups of G that you have, so let's say if H is if H is a subgroup of G, then H is nothing but of this form 1 z square up until z to the power p to the power some m minus 1. Now the fact is that the moment you take a subgroup, one has to be there, right? So one has to be there the moment you take a subgroup. And also the way the group is defined, if you want to construct a finite subgroup, the existence of inverses will make sure that z square, all these things are there in the subgroup. It's just basic group theoretic definition, right? So now what happens is that if it becomes infinite, if the subgroup order becomes infinite, then this subgroup itself becomes G, right? So then all the proper subgroups of G has to have of the form like this. And that makes sure is that if H is a proper subgroup of G, then H is cyclic. Okay, so this is one of the examples that you might try to keep in the back of your mind, is that there exists a non-cyclic abelian group of infinite order whose proper subgroups, all of whose proper subgroups are cyclic, and that is this group. And the subgroup of this group is precisely, every subgroup of this group precisely looks like this for some fixed m. Okay, so that's it for today. We will, yes, Pawan, hello. You have any questions or query? Okay, fine. So if not, and please check our IIT Jam Math crash courses for IIT Jam preparation. For that, you can actually go to our Chinta website and see it there. Thank you for joining. We will meet in the upcoming session with another problem. Oh, thank you.